Okay, welcome to Chapter 2. Chapter 2 is about derivatives, which is probably what most of you have heard about calculus in the past. So in our first lesson here, we've got a warm-up, and I want to develop the idea of what a derivative is. So what I want you to do is find the slope of the tangent. We're going to use just the basic parabola function here. And you're going to find the slope of the tangent at these 3 points, 2 numbers, and then just in general, we're going to sub in a for x. I want you to pause the video and do that on your own. I'll set up the first one for you, just in case you're not remembering to find the slope of the tangent. We're going to take the limit as h approaches 0, and here we've got the x value of 3 all over h. So pause the video at this point and go through each one of these 3 examples. All right, so welcome back. Hopefully you've gotten through those 3 answers. You're going to plug that 3 plus h into the brackets here and square it. So you're going to get 9 plus 6h plus h squared when you FOIL out the 2 brackets. And then when you plug 3 in, you're going to get a minus 9 as well. The 9s will cancel out, and then you'll be left with an expression that you can factor an h out of, which is nice. The h's will cancel out, and then you'll be able to take the limit with direct substitution. And you're going to get the answer 6 here. So I've skipped some steps there. Hopefully you've got that work. Let me know if you have any questions. In the second one, again, we can set this one up. We're plugging in -5 this time. And what we're looking for here are some shortcuts. That's what derivatives are all about. Like, how can I go through this work with a shortcut? Again, this time you would have substituted in -5 plus h into brackets. You would have FOILed it all out, and you would have come out with the answer -10. So we're talking about a parabola here, so you can imagine what this looks like. I've got my basic parabola, and what we're saying is that if you go over to x is 3 and draw a tangent line there, the slope of that tangent line would be 6. And if you went over to -5 and you drew a tangent line here to the curve, you would come out with the slope of -10 on that one. So it's going to be steeper. That makes sense to us, right? The parabola gets steeper as we head out from 0. Negative on the left-hand side and positive slopes on the right-hand side. This makes sense to us. In part C, I am going to go through all the steps here because we're going to look at in general. And this is where we're going to come out with like a shortcut for us. So I'm plugging a plus h in with brackets here. And then just a. And so I'll expand that out. When I do that, I'm going to get 4 terms when I FOIL out that bracket. And the middle 2 will collect, so a squared plus 2 ah plus h squared. And the order doesn't matter here. Maybe you put ha. A squared. Technically, since they're both variables, we don't have one as a coefficient or one as a variable, then you would have the alphabetical order. So I've got a squared minus a squared. They cancel out. And the expression that I'm left with here, I can factor out a common factor of h. And this is lovely because it's going to cancel out with my denominator. And now I'm left with an expression that I can actually just take the limit of. And so I sub in h is equal to 0, and I get 2a. So the slope of the tangent, what we're saying here is that the slope of the tangent for the basic parabola looks kind of like this. No matter what a number you pick, if you draw in the tangent, the slope is just going to be double the a number, right? So if I went over to 4, the slope of the tangent would be 8. And if I went over to 100, the slope of the tangent would be 200. So it gives us this nice quick shortcut to find the slope of the tangent. All right, we're going to move on to the main lesson. So we're defining the derivative function in this lesson. The derivative of f at x with respect to x. So this phrase here is just telling me what the variable is in the equation. We define that derivative function as f prime of x is how we read this. Or sometimes we say f prime at x, that's fine as well. So the derivative function f prime of x is actually just equal to the limit, and I'm leaving in x here when I take the limit of the difference quotient, just like we used to do. So the derivative function of f at the number a then is f prime at a is equal to, and again I would just take that number a and plug it in. So you guys are already used to doing this thing on the left. We used to call it the slope of the tangent at x equals a. But now we've got this short form notation. We like this a little bit better. It tells me what the original function was, and it tells me what number you put in for x, all in this one little notation. Whereas here I've kind of lost the information about what the function was. So sometimes we would actually write of f at x as well, which is kind of a long spiel that now we've shortened up. We know that this function gives the instantaneous rate of f at x. So therefore that derivative function f prime at x just gives the slope of the tangent for any value of x. So again, f prime at a is the same as the slope of the tangent at x equals a. From the warm-up then, we found that if f at x is equal to x squared, then the derivative function is f prime at x is equal to 2x, right? Just 2 times whatever the x number is that you plug in. Now there's multiple ways to write this notation. So I could write f prime at x. I like this one because it gives me lots of information. Tells me what the original function was. It was the f function. Tells me what number you're going to put in for x right there in the statement. Another notation you could use is just to say that y prime is equal to 2x. Usually we would only use this notation if the original equation was given as y equals. So if I gave you y equals x squared, you would use the notation y prime, for instance. We don't love that one. Again, I always prefer function notation because it gives me more information. A new type of notation, though, in derivatives is something that we call Leibniz notation. So Leibniz was an old mathematician that came up with this notation. Leibniz. And it's got this dy dx stuff. So when I read this first one, I say dy by dx. And over here, I would read this guy as the derivative, right? So the d here is telling me take the derivative. That's the numerator d. Take the derivative of x squared, because that's the function that's written here in brackets. So this is like telling me what the f is, right? So it's giving me a bit more information. So it's the derivative of x squared, and then the bottom here, the denominator tells me with respect to. It tells me what the variable is. Now in high school, most of the time we deal with equations in one variable. We're going to see an application using Leibniz notation later on in chapter 2, where we're given 2 different equations with 2 different variables. And then it's important for me to know with respect to which variable are you taking the derivative. This one here, I could also read this as the derivative of y with respect to x is how I would read this. And again, all of these things that I'm highlighting in green are equivalent. They just give me different pieces of information. And you always want to give me the most information that you can. So if you're given a question with function notation, you should be using the function notation. If you're only given y, then you can use y prime or dy dx. Again, both of these don't give me a ton of information. We won't use this last notation very often in this course, but it's going to come up in future calculus classes. So normally to answer questions like the warm-up, we would find f prime at x first. So I'm going to just head back to the warm-up. Notice that it was the last thing I did. I found f prime at x or f prime at a at the end here, and I came out with the answer 2a. But if I'd known that from the start, that the slope of the tangent was just double the a value, then this first question becomes quite a bit easier. It's just double 3. So I get 6, or just double -5, and I get -10. So in the future, we'll do the general equation first and then plug in numbers. All right, so heading into some examples, we're working on finding the derivative using first principles or using the definition of a derivative. Now, by the end of this unit, you're going to know other ways to find the derivative. So you're going to want to look for these phrases when you get to the review or the test. And basically what these 2 phrases mean are use limits. The whole point of this chapter is to come up with a bunch of shortcuts so I don't have to use limits all the time because it's a lot of work. So instead, we'll use those shortcuts. But whenever I see a question that has these phrases, it's telling me use limits. All right, so I've got f at x in my question, so I'm going to use f prime at x in my answer. I'm finding the derivative with respect to x of f at x equals, and I've got this root function here. I want to find it at two different values, but what I'm going to do is find it in general first and then just plug in the numbers at the end. So finding it in general, I just use my difference quotient, and I'm just leaving the x in there. So I'm going to plug x plus h into my function. And then just plugging x into the function, so the original function. All right, so now we're going to try to simplify this. We want to be able to take the limit at 0, but we've got that pesky h in the denominator. What I notice here is a couple of things. I can sort of simplify this first root by expanding the 2 into the bracket. Doesn't really help me. There's still no h to factor out and cancel. So I'm going to use the strategy because I have two roots in the numerator with an addition or subtraction. I'm going to use the strategy of multiplying by the conjugate. All right, so we're taking the limit of this whole big thing. All right, we've designed that numerator so that it's a difference of squares. So what's going to happen when I multiply out and I get these 4 terms, the middle 2 terms cancel out, and I'm just left with the first term, which is the first root times the first root. It's the same expression, so the root just cancels. You don't technically need these brackets here. And then I'm going to subtract. I've got, again, the middle terms canceled out. Now I just need the last term times the last term. Again, the roots cancel out. Don't forget that you're subtracting both of those things, so that this set of brackets is necessary. And then in the denominator, we're not going to simplify because remember, we're hoping that this h will cancel out. So I don't want to multiply it in. Plus, it doesn't really help much to multiply it in. All right, so now in the numerator, I've got 2x minus 2x, so that goes away, and then I've got minus 1, and I'm subtracting negative 1, so I'm adding 1 over here, so those cancel out as well. And I'm left with 2h up top. All right, now we've got 2 h's as common factors, top and bottom. They're going to cancel out. And at this point, I've come up with an expression that I can take the limit of. I'm all over the place on my tablet today. All right, so I can take the limit. I'm going to plug in h is 0. And what I get in the denominator here are 2 of the same roots, right? I'm just adding them together. So I've got, instead of adding 2 together, I'm going to say I've got 2 times the root. And then I've got a common factor of 2 on the top and the bottom that cancels out, and I'm left with 1 over 2x minus 1. You may not remember, but way up at the top there we had f prime at x. And so now we've got the derivative with respect to x. And so what I want to do next, the next thing the question asked me to do was find the slope of the tangent, or find the value of the derivative at x equals 1 and at x equals 5. So make sure you've always got this little dash here. It's like kind of like an apostrophe. to show me that you're finding the slope or the value of the derivative. So I'm just plugging 1 in now to my expression. And so I get 1 over the square root of 1, which is just 1. And then over here, and here I get 10 minus 1 in the root, so I've got 1 over the square root of 9, which is 1 over 3. And so it's telling me the slope of the tangent is either 1 when I'm at x equals 1, or the slope of the tangent is 1/3 when x is equal to 5. All right, on the next page of your note, we're talking about the normal of a graph. So the normal of a graph f at x at the point P is the line that's perpendicular to the tangent at the point P. So if I had a function that looks like this, and I ask you to find the normal at this point, you would find the tangent slope, and then the normal is actually the one that's perpendicular. So it looks like this, right? So this would be the normal. It's going to be perpendicular to the curve, basically. I'm going to use the notation here. I'm going to talk about the slope. So I'm going to say the slope of the normal, just using a subscript. It's related to the slope of the tangent. Remember, the tangent here is the one in red. If you might remember from grade 9 math, that to find the perpendicular slope, you take the negative reciprocal. So negative, and then you flip the fraction of the other slope. All right, so in example 2, we're asked to find the equation of the normal to the graph. We've got a reciprocal function here at x is equal to -1. So in order to find the equation of a tangent or the equation of a normal, I need two things. I need the slope and I need the point. So in order to find the slope of the normal, I'm going to find the slope of the tangent. And to do that, I'm going to use derivatives. So y prime is going to be the limit as h approaches 0. And I'm going to plug x plus h in here and x. Now I don't have function notation to write in here, like I can't say f at x plus h because there is no f in this question. So I am just going to go right into substituting. And that's all over h. All right, we're going to try to simplify this. So whenever I've got fractions within a fraction, usually our first step is to try and find a common denominator there. So I'm going to find a common denominator on the top, and then I'm going to just move this dividing by h. I'm going to change it to multiplying by 1 over h at the end. My common denominator is just going to be these two original denominators multiplied together. So my new numerator is going to be x plus 2, and then my new second numerator will be x plus h plus 2. Doesn't matter which order you write these two things in the denominator. The numerator matters because I'm subtracting all of these terms here. So I'm going to do that in the next step. And so in the numerator here I get x, and I see here that I'm going to be subtracting an x. So those guys are going to cancel out. And then I've got 2, and then I'm going to be subtracting a 2. So those guys are going to cancel out. And I'm just going to be left with subtracting h, or negative h, on top. And again, I'm taking the limit of this whole thing, both brackets being multiplied. All right, so this is when we can cancel out that pesky h in the denominator. That's what was stopping us from using the direct substitution to take the limit. So what I'm left with then is just -1 on top, and in the bottom those two brackets. And then I'll take the limit. So I have the same bracket twice in the denominator, so I can write that just as one bracket being squared. Okay, now remember that this is y prime, which is the same as the slope of the tangent, right? So we've got y prime here. That's the slope of the tangent. I want the slope of the normal, though. So, and I want to know what's going on at x equals 1. So for the slope, I'm going to say at x equals -1, the slope of the tangent is equal to, so I'm just plugging in -1 here into my expression. And so in the denominator here, I get 1 squared, which is just 1. Negative 1 divided by 1 is just negative 1. But what I want is the slope of the normal. So the slope of the normal is going to be the negative reciprocal of this. So I'm going to do negative 1, and then I'll flip this fraction. So instead of negative, it becomes positive. And when I flip the fraction, I get 1 over 1 is just 1. So the slope of the normal is positive 1. Now, in order to come up with the equation, I also need a point on the original curve. I want to know the point when x is equal to 1, or sorry, negative 1. So I'm going to figure that out. So I'm going back to the original equation here. And I get a 1 over 1, which is just equal to 1. Lots of 1's in this question. So you can be thinking here that the point then is negative 1 comma 1. All right, next we're going to find the equation. So for the equation, we've got so far that y is equal to, the slope is 1. Remember that was our slope up here, plus b. We're going to sub in that point. And so I get a negative 1 over here. I'm going to add it over to the other side, and I get b is equal to 2. And so therefore, so we had 1x, I've just started changing it to x, and then plus 2 for our b value. All right, the last part of our note here, we're talking about differentiability. So differentiability just means, can you take the derivative? So when I say something is differentiable, it means I can take the derivative. So f at x is differentiable. I can take the derivative of f at x equals a if f prime at a exists, which seems kind of obvious, right? But that's where we're defining that word differentiable. So f at x is differentiable at x equals a if you can take the derivative at a. So what does that mean? Well, it means then that the limit as h approaches 0 of the difference quotient when I plug in a exists. Now that also tells me if the limit exists, well, this part here, f at a, must also exist. It also tells me that f at x is continuous at x equals a. So I must have that the value f at a exists as well as the limit on both sides of x at a. So I have that the limit as x approaches a of f at x is equal to the value, the y value, right? So as I approach from the left and the right, the y value is the same, which also tells me that the left-hand limit is equal to the right-hand limit. So all of these things are true if f at x is differentiable at a. So as soon as a question tells me f at x is differentiable, I know right away that all of this stuff is also true. Otherwise, f at x is not differentiable at a, and we would say then that the derivative f prime at a does not exist. So what does that look like on a graph? If a function is not differentiable, and we're talking about here at x equals a in all of these graphs, it could look like a cusp, which is when a graph comes into a point. Now, a cusp could also look like an absolute value function, so it could look like just a straight v as well. That would also be a cusp. Another way a function could not be differentiable is when it has a vertical tangent. Sometimes we call this a scary slide, like you're coming down the slide, it just drops suddenly and then continues on its merry way. This is a vertical tangent. It kind of looks like a cubic function that's been rotated on its side. Another way that I could have a function that is not differentiable is if I had a discontinuity. So here I've got a jump discontinuity, and this function is not differentiable. Function is also not differentiable at other discontinuities, like a vertical asymptote, for instance. There's something else I wanted to say here. Oh, when I think about it not being differentiable, remember that I can connect that to the slope of the tangent. So when I think about the tangent at this cusp point, it doesn't exist, right? Because I'm not sure, like some people might draw the tangent over here as a negative slope tangent, and other people could draw it like this. It's almost like the tangent's kind of like swinging around this point. There's nothing to kind of hold it in place. So I can't really talk about the tangent at a cusp point. Here, when I think about drawing in the tangent, they've drawn it in here with this vertical line. A vertical line has no slope, right? It's an undefined slope, so it's not differentiable as well. And then here as well, if I think about the slope of the tangent, well, on the left-hand side, I've got this tangent here. It's approaching a different amount, and then on the right hand side something different is happening again. And of course f at a does not exist, and in order to have a function that's differentiable, the point has to exist. For each of those functions above, the derivative does not exist at x equals a, and I would say the function is differentiable on x belongs to a set of real numbers such that x does not equal a. So it would be the entire domain. Another way to write that would be negative infinity to a and a to infinity, or you might use the union symbol in there. That's fine as well. And that's it for the first lesson for chapter 2. Enjoy your homework.